I think we can start. So, good afternoon. So today we're going to start the new chapter on electric potential. And I want to start by doing some conceptual discussion because some of the stuff that you're going to see here, you have already seen in mechanics or something very similar. You have already seen mechanics, but there are some conceptual difficulties which might lead to confusion. So I want to at least state them and see if those confusions, if you have those confusions, and try to resolve them that way. Okay, so we have three concepts this chapter: the electric potential, or I'll just call this potential, potential energy, and potential difference. So we could, of course, call this electric potential energy, and electric potential difference. Now, these are related to each other, but they should not be confused with each other. They are equivalent to each other. In particular, this one is going to perhaps cause some problems, but this also can cause some problems, right? Now, of course, we could also have the difference in potential energies, and we could also have potential energy difference, but I'm going to leave that for later, perhaps. Right? So these have different symbols. So this is denoted by a V, which leads to some further confusion because it's the same symbol for its unit. So potential is measured in volts, and the abbreviation for volts is this capital V. Potential energy, we'll generally use U. Okay. But sometimes, again, in some books, you might see V or other symbols. And for potential difference, we're going to use delta V. Okay. So potential difference is exactly what it sounds like. It's the difference between the potentials at two different points. Okay. It is not the difference between potentials for two different charges. When we refer to a potential difference, we generally refer to the potential difference between two different points in space. Okay. It could, of course, also be the potential difference from one time to another, but generally this is a difference in space. It's not difference between different particles. Okay. The potential energy is what I want to start with. This is very similar to the potential energy you already know. So in mechanics, you had potential energy, and that was gravitational potential energy, right? So how did you define potential energy in mechanics? There are different ways, but one of them that I like is for energy itself, in fact, is the ability to do work, right? So this is some. So if your system has some potential energy, then it can, in fact, turn this into some work. It can do some work on some other systems, right? Or if you just let it go, it will typically turn its potential energy into kinetic energy. Right? And the typical example is that something in the gravitational field, this is potential energy. If you let it go, it's going to gain some kinetic energy, and its potential energy is going to decrease. Okay? And so let's now connect this to potential energy difference, which will denote by delta U. Typically, you can define the zero of your potential energy arbitrarily, right? And there are some general conventions, but it is really up to you. And the important thing is going to be the potential energy difference, right? It doesn't matter what the potential energy of this marker here is or over here, but the difference is what makes what determines the outcome. It is the difference between these 2 points, the potential energy difference between these 2 points, that determines kinetic energy, or the increase in kinetic energy as it moves through this motion. Right? So this is the idea. Now we're going to have something very similar for potential and potential difference. And yeah, the way to develop this is typically through with analogies to potential energy and potential energy difference in mechanics. But the electrostatics, the potential itself has some peculiarities of its own, and it is going to be related to some concepts that we recently learned, electric field. So it is a concept of its own, but the pedagogical way to approach this is to make an analogy with the potential energy. So, right. Now, how did this potential energy was defined? So potential energy in mechanics was related to gravity. Now it's going to be related to electric force. Okay. Now, I don't know if you recall the relationship between the force and the potential energy, but one determines the other. Okay. So this marker, we say it has some potential energy because it's feeling the gravitational force. right? And if it moves along the force that it feels, then its potential energy is going to decrease. Its kinetic energy, if there is nothing else acting on it, is going to increase. Right? So the same deal here. The electric force, it turns out to be, this is a conservative force. Has a potential energy associated with this, and it's electric potential energy. And the same thing happens, right? So if you have some particle and there's some electric field, let's say that we have some electric field over here, and you have a charged particle, it's going to feel a force because of this electric field. And if you just, put a charged particle in an electric field and just, apply no other forces on this, it's going to accelerate in accordance with the forces, the electrostatic forces acting on it. And then its potential energy is going to decrease, and its kinetic energy is going to increase, just like a marker pulling down in the gravitational field. Now, the difference in the electrostatic case is that this is not necessarily going to go in the direction of the electric field. The behavior depends on the charge in two ways. First, the larger the charge, the larger the acceleration, because the larger the force, and you don't need to change the mass. In gravity, there is this peculiarity that the acceleration is proportional to mass, but the force is also proportional to mass. So given a gravitational field, if you put an object there, regardless of its mass, it's going to have a unique acceleration, right? Not so with the electrostatic field. And, if you put a charged particle in an electric field, it's going to have an acceleration proportional to its charge. Assuming, of course, you're not just replacing one electron with two electrons, but you're replacing something with 1 coulomb charge with 2 coulombs charge, but the same mass. Right? If you're really doubling everything, including doubling the mass, of course, it's going to have the same acceleration. Now, the second thing is that this can go two ways. In the gravitational field, everything moves the same way. Right? The gravity is downwards on the surface of the Earth, everything falls downwards. In an electric field, positively charged particles are going to behave differently than negatively charged particles. They're going to accelerate in opposite directions. This is not something you can see in gravity. In gravity, everything accelerates the same direction. But apart from these two peculiarities or two differences, everything is the analog. The important thing that if you put a particle in a conservative field that's related to a conservative force, if no other forces are acting on it, the potential energy is going to decrease. The kinetic energy is going to increase. This is what happens. Okay, this does not change. It could be moving in the opposite direction, but its potential energy is going to decrease, and its kinetic energy is going to increase if there are no other forces acting on our object. Right? This is something to keep in mind. This is like your guiding principle when you're looking at whether the potential energy is increasing or decreasing, and so on and so forth. Now, to make things a bit more, well, do you have any questions? I'm moving at a certain pace, but I'm not really sure if you're following. Perhaps I said something confusing. Are there any questions? Someone wrote something. Is this class going to be online during semester? Yes. Are there any questions related to what I'm saying? So let's make this.
Dönem boyunca tüm dersleriniz hep online mı olacak?
Bunu sonra konuşabilir miyiz? Do you have any questions about physics? So let's make this a bit more formal. Now we can relate the potential, the force to the work done, and hence the potential energy. So let's first let's say that we are going from A to B. Okay, maybe just change my markers. I'm going from A to B. So there's going to be a change in my potential energy. So my delta U is going to be my final potential energy minus my initial potential energy. Now this, as you might remember, is going to cut. This has a number of forms, but we generally write it like this. From A to B. Now, if we have a uniform force, and if we are moving on a straight line, then this simply turns into minus F times T. So this is the distance that you travel. This is the force that's the magnitude of force that's applied on you, and there's going to be some change in your potential energy. This change in potential energy is, in general, if there are no other forces, is going to be something negative. Right, and this is also, of course, sometimes written as minus W. So this is the work done by what? Who's the agent that's doing the work here? So there are two possibilities. Is this the work done on the particle, or is this the work done by the particle? Furkan Ayıldız, what do you think? Furkan, are you with us? Okay. What about Bora? Bora Ölçeken? Okay, Furkan says he doesn't know. Bora, do you know? Work done by the particle. Okay, can you convince me that this is the work done by the particle? So this is the first possibility. The other one is on the particle. How would you convince me? Can you not speak? Timur, can you speak? It will go much faster.
So the electric field does the work.
Electric field does the work.
And
then why do you say by the particle?
Particle does the work, but it's negative, and for electric field it should be positive.
Okay, but this one, so if I write it this way, is this work done by the particle or on the particle? This makes a difference in sign, right? So if you give the wrong answer, it's just wrong. And sometimes, in the exams, people make this mistake, and then a lot of points are taken off, and they object, I just made a sign mistake. But conceptually, it's a completely different thing. Is it the work done by the particle or on the particle? Now, this is a convention. This is not something you can logically deduce, right? It goes back to the derivation of this in mechanics. And if you don't recall this, you should go back and check that out. Now, this is the work done on the particle by the force. On our charged particle by the force, by our electrostatic force in this case. So there are some other particles that creates an electric field, so that exerts the force on this particle, and that particle is going to change its kinetic energy. There's some work done on the particle, and this work is the expression for that one. Right. So as I said, I'm not going to repeat this. This is something you must have covered in mechanics, and if you don't recall that, please go back and review that. This is going to be important when you're looking at problems with some moderate degree of complication. To understand what's going on, it's going to be very important. You can't do this blindly. If you're doing this blindly, you're just basically tossing a coin. It could easily go wrong. Yeah. Now, what we want to do is that we want to change this a little bit. Right? So this force here, this force is our charge times electric field, okay? And depends on the charge. Now, we don't, in electrostatics, we kind of prefer to work with the fields, right? Fields are easier to handle because they do not depend on the magnitude of the charge at a given location, right? We can put any test charge over there, and knowing the magnitude of the electric field, we can calculate its force. Whereas if the forces are given, then you need to know the charge to go back to field and to calculate the force on something else. So fields are a little bit more fundamental for practical reasons as well as for deep physical reasons, but we want to express this in terms of electric field. So what we do is that instead of writing it like this, we divide things out by the charge. Okay? And we simply define the electric potential at a given point there's the potential energy of a test charge at that given point divided by the magnitude of this test charge. Okay? This is definition. There is no complicated way to drive this. It's just a definition. It is what it is. We could in fact use some equivalence sign over here. Now, this is potential energy. So it is units of joule. This is charge. It has units of coulomb. This joules per coulomb as the unit volts. And the abbreviation for volts is a capital V. Okay? So this is something I'm guessing a lot of you are familiar from everyday life. Like you have batteries that charge at 1.5 volts or 9 volts or something like that. If it's a cell phone battery, it's probably around 5 volts. And you have the electricity coming from the outlets. That's typically 220 volts or 240 volts. Or if sometimes it's 208 volts for some technical reasons. And you have car batteries. It's, I don't know, 12 volts, something like that. But the volts is what we're typically familiar with. And this is very, very convenient because we are not going to refer to the potential energy stored in a battery or something like that. We just refer to its potential difference that it provides. And you're done. You just we have some universal tool to talk about the batteries. Now, something important here. Okay? So there is a difference between this and this. And when you talk about the batteries, you have a 12-volt battery. What does it refer to? What is that potential? Any suggestions? So we have a 12-volt battery. So something is at 12 volts potential. What is that? So if I say that this marker has I don't know, 5 joules of potential energy, what is missing in this description? Can this marker have 5 joules of potential energy? And if, for example, I'm saying this has 5 joules of potential energy, but Emre is saying no, it has 15 joules of potential energy, how would you decide which one of us is saying correct thing? How would you approach that argument?
Maybe we should decide a reference.
We need a reference point. Very good, right? So this could have 5 joules of potential energy with respect to a point just below it, and 15 joules of potential energy with respect to a point just further below, right? So you need to decide with respect to what point you're measuring your potential energy. Now, for a battery, if a battery has 12 volts of potential, if it provides 12 volts of potential, what does that mean? A battery has 2 terminals. There are some batteries have multiple terminals, but typically a battery is going to have 2 terminals. So what the battery is providing is not potential, but potential difference. It's the potential difference between 2 terminals. Okay? So those 2 terminals are going to be at different potentials. But it's kind of meaningless to speak of the potential of a single point, just like it's kind of meaningless to speak of the potential energy of a single point. Okay? A single point mass can never have potential energy. I'm not talking about gravity mechanics, right? So a single point mass is never going to have potential energy. You need multiple masses to have potential energy. One of the masses is going to create a gravitational field, and that gravitational field is going to have some force acting on this second particle or our original particle, and there's going to be some potential energy associated with that force. So you can drive the potential energy from the force, or the potential energy difference as you move from the force, or you can drive the force itself from the potential energy. Right? So this integral relation example, can be inverted. I suppose you must have done that in mechanics, but the relationship looks like this. The x component of the force is going to be negative, the partial derivative of the potential energy with respect to the x coordinate. And so this one inverts that one. So just like that, you can't have the potential without defining some reference point. Now, there are some conventions for defining this. One convention is taking the potential at infinity to 0, but that's not the only convention. Okay? Another convention, for example, is if you have a circuit, is to keep your ground at 0. And that's typically the negative terminal of your battery. That you connect the battery to your circuit, and you say that, okay, the negative terminal of this is at 0, the positive terminal is at 1.5 volts or 5 volts or whatever. So this one, this definition gives you something volts. This one, the potential difference is also going to be in volts, right? Obviously, if you have some point that, I don't know, by definition, by our choice at 0 volts, and then something is 12 volts above this, then the difference is 12 volts, but at the same time, the both of these numbers have the units of volts. Okay, now, since I really cannot see your faces, I don't know if you're confused or this is something trivial. It's a bit frustrating. I can just see one person. But if this is confusing, you should really stop me, because you shouldn't be thinking about these concepts as you're trying to solve problems. And there are a lot of concepts that have similar names, but have completely different meanings, and it can cause some trouble. Now, I want to look at one of the examples in the book. In fact, the first example, the first conceptual example, negative charge. Suppose a negative charge, such as an electron, is placed near the negative plate in figure 22-1 at point B, shown here in 2, okay. If the electron is free to move, will its electrical potential energy increase or decrease? How will the electric potential change? Okay, let's do this. Let's see if we can figure this out without getting ourselves too confused. So we have parallel plates, oppositely charged. So this creates an electric field between them. So one plate like this, you can see one plate like this, another one like this. Which one is positively charged? The one on the left is positively charged. And this is negatively charged. So I have some electric field that's produced by these charge distributions. And I have an electron at this point B. And here's an electron. And they're asking if the electron is free to move, meaning there is no other force acting on it, will its electric potential energy increase or decrease? How will the electric potential change? Okay. So is delta U positive or negative? Which one? And what about the change in the potential? I have something over here. So what's your response to the first one? What would happen to its potential energy? This is something I said already at the beginning. So what does happen to a marker in a gravitational field if there is nothing else acting on it? What does happen to its potential energy? It will decrease. So will this. Okay. That's what the conservative force does. If the only thing acting on your particle is a conservative force, there's some potential energy associated with it, then its effect is going to be decreasing its potential energy, increasing its kinetic energy. That's it. This is always what happens. So if you put an electron here or here or here, it doesn't matter where you put it. If the only force acting on it is electrostatic force, then its electric potential energy is going to decrease. Now, its potential is another story. Okay? So this delta V, given by our definition, is going to be delta U divided by charge of the electron. So this one, change, so the correct answer is on. but the charge of the electron is going to be is negative. Right? So if this one is negative, if my potential energy is decreasing, then I must be moving in a way that increases my potential. The final point I reach is going to have a higher potential than my initial point. My potential energy is going to decrease, but I'm going to end up at a higher potential. I'm going to end up at a lower potential energy, but at a higher potential. Why? Because of this relation. If I'm negatively charged, then a decreasing potential energy corresponds to an increasing potential. So if a positive charge did the same thing, then it will be the opposite for the potential energy. Okay? So this electron, is going to feel a force to the left. Right? It's going to feel a force. And if I just let this go, it's free to move, then it's just going to move towards the positive plate. Now, if I take a positively charged particle, and again, start at this point and move it to the left, its potential is still going to have the same change. Right? Its potential is going to increase. This electron's potential energy is decreasing, its potential is increasing. If a positively charged particle did the same thing, the potential will still increase, but its potential energy, the potential energy is decreasing, its potential is increasing. For a positively charged particle, the potential would increase, and so would its potential energy. It will, in fact, feel a force opposite to the electron, and so its motion, if it's imitating the electron, will be against the force. And what does happen when you go against the force? Gravitational force is downwards. If something is moving upwards, its potential energy increases. So if you're moving against the force, your potential energy increases. Whether your potential increases or not depends on your charge. And if it's positively charged, then your potential energy is also going to increase. So your potential is also going to be increasing. So the potential is independent of the charge. As you move from one point to the other, the potential is changing. It's changing the same way for all the charges. The change in potential energy depends on the charge. If the charge is positive, the sign of the potential energy change is the same as the sign of the potential change. If it's negative, it's the opposite. Okay, let's do something quantitative. Let's look at the next example. Go ahead.
Could you please briefly explain again about the potential energy?
Okay. So,
as far as I understood, you said that just because of that electron is going to feel a force towards the positive plane. Am I right?
That's right, yes.
And because of that, it's going to move towards the left. So its potential energy is going to increase.
No. Its potential energy is not going to increase. It's feeling a conservative force. It's moving only under the influence of this conservative force. This means its potential energy is going to decrease. This is the same thing as freely falling in the gravitational field. You're only feeling the gravitational force. You start at rest. What does happen? You fall down and your potential energy decreases. It's the same thing here. This electron is feeling some force. In fact, it's feeling a constant force because it's a constant electric field. And it's going to just fall down. Its potential energy is going to decrease. Its potential, however, is going to increase. It ends up at a higher potential than it started with.
So the potential energy increases, but the potential increases.
No, the potential energy decreases. So this is the same situation. Really, the analogy is very strong here. Right? This is the situation, is something just falling in gravitational field. What does happen to its potential energy?
Hocam, can we please give numerical values? Because I'm having a hard time understanding.
Okay, let's say that it starts at some potential of 1 here. Okay, so V is equal to 1, and then it ends up at V is equal to, at a higher potential, let's say 4. okay, over here. So we start at B and end at A. We are going from B to A. Right? So this is in volts. Now, the potential energy is going to be Q times V. So the potential that we started with is going to be the charge of the electron times the potential over there. And the potential energy we end up with is going to be the charge of the electron times the potential there. Yeah. Now, charge of electron is something very small but negative. Yeah. So this is going to be some Q, some positive number. I'm just going to put negative sign here, make things positive, times 1. And it's going to be some minus Q times 4. This Q is positive. Okay, this Q is the absolute value of the charge of electron. So this is minus Q, this is minus 4Q. I went from here to here. Did my potential energy decrease or increase?
Decrease.
It decreased, right? From minus Q to minus 4Q. Q is a positive number. What happened to my potential? It increased. It went from 1 to 4. Why? Because these have the opposite behavior if your charge is negative. If the charge was positive, then they will have the same behavior. When one is increasing, the other will also increase. Okay? But this is too convoluted. There's a simpler way to look at this. If you have, okay, let's try to look at this another way. I have an electron here. It's at rest initially. Okay? And there is this electrostatic force acting on it that accelerates it to the left. Right? What is going to happen to its kinetic energy? It starts at rest, it's accelerating. What happens to the kinetic energy?
It's supposed to increase, right?
It's going to increase, but energy is conserved. If kinetic energy is increasing, potential energy must be decreasing. There's no other way. This is a conservative force. Electrostatic force happens to be a conservative force. It has the same form as gravity, which we have already shown is conservative.
And can I ask one more thing?
Yeah, of course.
So, according to this planar plane, the negative one, it's like has less potential, but
That's right.
the positive one has more. What is it? Is it like a rule? The positive one is supposed to have a higher potential, or if it's
Yes.
a rule, why is that? Where did it come from?
Yeah, so this is because we didn't do this yet, but so as you go from one location to the other, to calculate the potential difference. So to calculate the change in potential energy, you did this, right? As you go from one point to the other. To calculate the potential difference, you do this. So you are moving along the electric field. And if you move along the electric field, you find that the change in the potential is going to be negative. And so let's say that you move this, and your dl is going to be this little thing. The dot product is going to be something positive, and the whole integral with the negative sign in front of it is going to be something negative. As you move along the electric field lines in the direction of the electric field, you're moving from higher potential to lower potential because of this definition. And this comes from this. It's just you take this and you divide everything by Q. Right? There's nothing mysterious. It's not a coincidence that they look exactly the same. You just start with this one, divide out by Q, and you obtain this. And this integral dictates that as you move along, it's going to be negative. Right? It is a rule, but there's a reason for it.
Okay, I got it. Thank you.
Any other questions? So this, in fact, is the next thing on our agenda today. That this relationship between the potential or potential difference and the electric field, and this relation is given by this. Right? Now let's do a numerical example. So that there's a example 23-4 charge conducting sphere, and you have a sphere. So let's read this. Determine the potential, the distance r from the center of a charge conducting sphere with radius r naught for r larger than r naught and r equals r naught and r smaller than r naught. The total charge on the sphere is capital Q. Okay, so let's try this. So we're going to utilize this. Okay. And we're going to make some analogy with this one. So we have some charge sphere with some charge Q and some radius R0. Okay. And we have some distance R from the center. So that there are a number of situations where R is larger than R0 or R0 and R is smaller than R0. We are required to determine the potential. Yeah. Well, we can only, of course, determine the potential relative to some point, and here they're not telling you this explicitly, but we are going to choose that our potential at infinity is 0. So far from all the charges in our problem, we are going to assume the potential is going to be 0. This makes sense that if you're far from all the charges, we make equal potential there, it's not going to feel, if you put a charge there, it's not going to feel any force. It makes sense to call its potential energy to be 0. It's just, you could also call it 5, doesn't matter, but 5 is a little bit weird. 0 is the nicer number. Okay, so we're just going to choose this. All right, so how would you calculate the potential at this point? How do you approach this? So this is kind of also a clue. It's like a tip. So how would you approach this problem? Where would you start? And we're going to use this. To use that, you need to know the electric field. Okay. What does the electric field of a conducting sphere look like?
After we pass the surface, is going to start decreasing non-linearly, so we can calculate it from the Gauss's law.
Do you know how nonlinear that changes? What's that nonlinear relationship? Okay. How about Pilin? Pilin, are you with us?
Yes, teacher, but I don't know, unfortunately.
You don't know. Okay. Well, a conducting sphere, if there's some charge on it, is going to have all this charge come to the surface and then distributed uniformly. It will become a spherical distribution. And a spherical charge distribution to the outside looks like a point charge at its center. Okay, so the electric field is going to look like this: 1/4πε0 Q over R squared. And its direction is going to be radial. It's going to be outward because this is positive. All right, so how do we use this? How do you use the electric field and utilize this formula? What you need to do is that you start at a point where you know the potential and approach this point. Now, because electrostatic force is a conservative force, it doesn't matter what path you take. Okay? So I'm going to start at infinity and reach this point, but I could come, like this, or more simply, I could come from a straight line from infinity. Right? Both are going to give the same answer. This one is going to be a Fourier integral. the argument inside the integral is going to be more complicated, but when you integrate it up, it's going to give the same answer because electrostatic force is a conservative force. Of course, taking this straight line is going to be much easier. Okay? So you take this, you put this in, you take the dot product, so your dl is going to be minus r and so on and so forth, and your potential at r is going to be q by 4 pi epsilon naught times r, when r is larger than r0. Now, when you reach r0, you're going to be, on top of these charges that are at the surface of this. This is a sphere, right? The spherical shell. Yeah, it's a sphere. You're going to be on top of the charges as you reach r. So how will you calculate the potential in that case? So let's say that you're just outside the sphere, and all these charges are accumulated on the surface, and you go from here to here. Can you have a big jump in your potential? Can your potential be discontinuous? Or does it have to be continuous? Now, if you rewrite the potential integral, we can turn it into a differential form. So as you move from two neighboring points, the change in the potential energy is going to be just F dot dl. Okay? So the integral formula is just taking this and integrating both sides. But for two points that are very close to each other, the potential difference between them is going to be this. Now, can this be finite? If the potential can be discontinuous, then this can be finite. That can't be. This is infinitesimal. Unless this is infinite, which is not physically allowed, then this has to be infinitesimal as well. It can't make a finite jump. So the potential has to be continuous. So at r equals r0, it's going to have 4 pi epsilon naught as well, by continuity. And the continuity follows from this. Because we don't have infinite forces in physics, that this has to be, the change in the potential has to be infinitesimal. It can't be finite over an infinitesimal position change. And now what about inside? Zero. What about inside? If you're inside the sphere, electric field is 0. So if you rewrite this formula, that your delta V is E dot dl, if this is 0, then this is all 0. Meaning that no matter how you move in a region with no electric field, your potential remains the same. It's just constant. So throughout inside, it's going to be Q by 4 pi epsilon naught r0 as well. So if you draw this, something constant and then decreasing as 1 over r. So this is 0, and this one is just, let's call this V0. This one is the surface value. It's the same inside the connecting sphere, and as you leave the surface, it just decreases as 1 over r, this formula over here. And now, utilizing this for arbitrary geometries can sometimes get confusing. Okay? When the electric field changes direction, when you're not going from infinity to finite point, but from finite point to another finite point, and so on and so forth. And in fact, I made a video on how to handle this dot product and what's the meaning of this in some detail. And I'm going to, it's already on YouTube, but I'm going to put a link at the end of this video, or description perhaps, when I put this lecture up. Okay? I suggest you go watch that, solve some problems, and perhaps you're going to still have difficulties, then come ask me questions. Okay? If you're not having difficulties, that's fine, but there is a chance that you're not having difficulties because you're not trying difficult problems. Right? So try to break yourself a little bit. I'm not completely. If you have no clue, then you can't ask questions, but something intermediate. Hopefully you know what I mean. Yeah, go ahead.
Sorry, I missed which video are you talking about?
I'm going to put a link.
On the opticals.
I made a video specifically for what's the meaning of these dot products and these DL and so on and so forth. So I'm going to put a link to it when I put this up on YouTube or perhaps put it on opticals, something like that.
Okay, thank you.
But this is not trivial, and the only way you get the hang of this is solving some problems and then thinking about them. And hopefully you'll have some difficulty and you're going to have some questions for me. So is there another? We can look at breakdown voltage, but I'd rather just very quickly look at the other section. So I already said this many times last time. There's this Newton's theorem in gravity that symmetrical distribution of mass acts like a point mass at the center, and there's the analog in electrostatics. A spherical distribution of charge acts like a point charge at its center to the outside. Okay? So this is the potential of a spherical charge distribution, and so it is also the potential of a point charge. Okay? You can do this more formally by you can take the integral and so on and so forth, but there is no need. We already solved this problem, and we already know that for all physical purposes, which is dictated by electric field and force, it behaves like a point charge at its center. So the potential of the point charge must also look like this. So the potential of the point charge. Now note that this can have a sign, this can be positive or negative, but it can't have a direction. Potential is a scalar. Okay? And this is its pros and cons. Now, because it's a scalar, it doesn't contain as much information as electric field, but it turns out that if you know the potential everywhere, then you know the electric field everywhere, because doesn't just have the information at a single point. You also have the information from neighboring points, and you can take derivative. Why does this work? Why you can represent everything you know about the electric field by a scalar potential? Does anyone know the answer? So this doesn't happen for every field. Not every field can be derived from such a potential. Not every force field can be derived from a potential energy. Right? So the relationship between the potential and the electric field is the same as the relationship between potential energy and the force. So what unique relationship do you need? What kind of property do you need for a potential energy to exist? It has to be a conservative force. Right? So the electric field happens to be a conservative field. So it can be derived from potential. So this, even though it's a scalar, contains as much information, when you know it everywhere, contains as much information as the electric field itself. You can use it to drive electric field, as we're going to see on Friday. Now, we can use this to make some calculations. So there's an example here for the breakdown, and there's a potential above two charges. So let's just get this example 23-6 very quickly. Now, this is titled Work Required to Bring Two Positive Charges Close Together. What minimum work must be done by an external force to bring a charge Q equals 3 microcoulombs from a great distance away to a point of 0.5 meters from a charge capital Q equals 20 microcoulombs. Okay, so I have Q equals what? 3 microcoulombs? Yeah, 3 microcoulombs. And I have capital Q, that's 20 microcoulombs. So Q goes from infinity to half a meter to this capital Q. And this is done by some external force. Obviously, these are both positive charges, they will repel each other. So you need some external force to bring them together. And they're asking for what's the work done by this external force. Okay. So you notice that a lot of things seem to be missing in this problem. So, okay, this comes from a far distance, but what kind of path does it follow? Turns out it doesn't matter. It doesn't matter at all. Now, how would you solve this problem? So they're asking for the work done by the external force. And we know charges, the initial configuration, and the final configuration. You have seen this before. You have seen very similar problems in mechanics before. There is an idea that you can utilize to solve this problem. What is that idea? So given configurations, what can you calculate? And what quantity can you calculate that's related to the work done? What is work equal to? So I've written stuff here and then I erased them. This F dot dl integral, the negative sign in front, is equal to minus W, but that was also equal to something before. What was it? Change in potential energy. Okay, it's the work energy theorem. The work done on a system by a conservative force is going to be equal to the change in its potential energy. Right? And given the configurations and the charges, you can calculate the potential energy. The initial potential energy is 0. These are infinitely far away from each other. The final potential energy, well, they don't have to be 0. You can choose the 0 potential energy anywhere, but that's the traditional choice. The final potential energy is going to be the potential of one of the charges, or the potential created by one of the charges, times the other charge, what we would consider as test charge. Okay. So if this is my potential created by my capital Q over here, 20 microcoulombs, initially my potential energy initial is going to be Q times V initial. And it's just Q, Q by 4 pi epsilon naught R, where R is infinity, that's 0. Okay. Just follows from our assumption that if you choose potential of infinity to be 0, we get the simple expression for R. Now, your final is going to be Q times V final, and it's going to be Q, blah, blah, blah. And you need to calculate this. You need to plug numbers in, multiply the charges, divide by 4 pi epsilon naught, and half meters. And that's going to give you some potential. Now, is this work done by this external force, positive or negative? Pretty much everyone gets this, right? Work energy theorem, delta U equals W, blah, 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 blah. And then, so one of them is 0. So is it 0 minus this number you calculate, or this number you calculate minus 0? Is the work done by the external force positive or negative?
Negative.
Why is it negative?
I don't
That's the
know.
danger of answering questions I ask. I always ask why.
I just say that with my intuitions.
You don't need your intuition though. That's okay. You should always try to answer, but you actually know this. Now, is your displacement in the same direction as the force? So how is the work done defined? It's the integral of force dot dl. So that dl is your displacement. If the force applied is in the same direction as displacement, then it's going to give something positive. If they're in opposite directions, then it's going to be something negative. If they're roughly in the same direction, then it's going to be positive. If they're roughly in the opposite direction, it's going to be negative. Is this force in the same direction as your displacement? That's the key to this question. And the answer is yes. Right? You had this capital Q sitting here. You had the small q. Some external force was acting towards this positive q because they were actually repelling each other. That force must be opposite to electrostatic force. And it brought it from infinity to some half meters. That force was towards the capital Q charge, and displacement is also in the same direction. So that product is going to be positive. So that leads to positive work done. You could, of course, do this using some formulas, but you always forget, what is going on. Whether the written formula is for the work done by the electrostatic force or by the external agent, by the charge on the charge, blah, 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 blah. The other one, the definition of work done, the integral of f dot dl, is, for me at least, easier to remember. So if you remember that, if you think about the physics of the problem, you should be fine. The book solves it a little bit differently, but it, of course, gets the same answer. All right. So I'm going to stop here.